Good morning, my name is Alfonso Mascareñas González and I'm going to present you the work entitled Heterogeneous Multicore SDRAM Interference Analysis. The plan of this presentation is the following. First, a brief introduction and description of the work objectives. Afterwards, an explanation of the key aspects to consider when dealing with SDRAM memory interference in heterogeneous systems. Besides, an explanation of how data is obtained is given. Posteriorly, it is explained how the interference calculation depends on the multiple SDRAM controller behaviors and that each of them is described by an equation. Then, some results are shown. The presentation is ended with a conclusion and future objectives. The use of multicore platforms allows us to have more throughput and a better swap. In other words, a reduction of size, weight, and power. All this is achieved thanks to resource sharing by the cores. Nevertheless, this sharing may provoke interference in different places of the platform. An example is depicted in the image at the right. In here, we assume that the cores share a level 2 cache as well as the main memory. This work focuses on the memory interference, more specifically the DDR3 SDRAM interference. This interference may not be a big problem in many systems. However, in the context of real-time systems, a response within an imposed deadline is vital to assure the correct functioning of the application. In these time-sensitive systems, it is very important to know what is the worst-case execution time of your application and how to reduce it at its minimum. This work has 4 objectives. The first one is to identify those aspects that play an important role in the SDRAM interference. The second one is to elaborate the necessary equations to estimate the worst-case SDRAM interference according to the previously identified key elements. The third one is to check the function's output by taking measurements directly from a heterogeneous multicore platform. The fourth and last is to compare the theoretical and measured interference impact of the different equations among themselves. The elaboration of equations that can estimate the SDRAM behavior relies on 3 aspects. Firstly, the SDRAM memory itself. The JDEC specifications related to its operation and addressing organization must be taken into account. Secondly, the memory controller used to manage the memory requests. Entries may be added in or out of order, and usually issued out of order. Thirdly, we have the platform heterogeneity. The multicore platform architecture and different types of processors affect the general behavior of the SDRAM. The SDRAM can be seen as a 3-dimensional array made up of columns, rows, and banks. The following image represents a 2-dimensional array made up of columns on the x-axis and rows on the y-axis. The black boxes represent blocks of memory. We have to still consider an additional logic layer, the banks. This can be kept open, all of them, at the same time, what allows us to interleave among them. This example shows 4 banks, which is acceptable for the DDR2, but not for the DDR3, which only admits 8 banks or 16 if we are using 2 ranks. It is important to note that we can only use a row within a bank at a time, so if we want to use another row, we must deactivate the current row and activate the new one. As we will see later, the way we access the SDRAM determines the overall behavior of the memory controller. We have seen how the SDRAM memory is organized. Now I'm going to explain how it works. It can be said that the SDRAM is made up of states. The commands are basically the instructions that the memory takes in order to execute a memory operation. They determine if we are changing the state or not. The timing is the number of cycles the commands require for its execution or to change the current state to a new one. For the purpose of this paper, we can stand out the following 4 commands. The read, which just loads the data, the write, which stores it, the pre-charge, which deactivates an opened row within a bank, and the active, which opens a closed row for a given bank. As for the timings, we can point out the following ones. Firstly, we have the operation execution itself. For example, when we read or write, we have to wait a certain number of cycles since the command execution until the data is available. Secondly, we have the timings associated to a state transition. For example, when we pass from a read to a write and vice versa. This is called the turnaround time, which is an extra cost to consider. Here we have an example of this. Let's imagine that we start with a read, then we continue with another read, but after that we want to execute a write. It is in this change of state when we suffer this turnaround. Other transition timings are the read-write to pre-charge to active, and finally the active to read-write. This occurs when we are switching to another row within a bank. The example at the right depicts this situation. If we assume that we are currently working with row 2 and we want to perform a write to row 3, we will first need to carry out the pre-charge and the active commands. The memory controller is the one that delivers the commands to the SDRAM memory device as function of the received requests. Normally, the controller is made up of queues, sometimes called FIFOs, where the commands or the data are stored, and schedulers that are used for reordering. The most important queue is the command one, which has a specific size which changes depending on the manufacturer. In here, requests are enqueued and reordered according to a logic. This logic is heavily impacted by the memory address we intend to access, as we will see later. It must be remarked that occasionally the read commands have higher priority than the writes in order to reduce the processor's stalling time. The platform heterogeneity plays an important role in the command FIFO enqueuing. Nevertheless, its impact is not generalizable and will vary from one platform to another. In this work, the multicore platform Keystone 2 by Texas Instruments has been used. About this complex platform, there are two aspects to point out. Firstly, the processor's type. Keystone 2 works with both ARMs and DSPs, which have different performances depending on the situation. The instructions pipelining must be analyzed in depth, especially how the out-of-order execution works for the loads and stores, which includes the study of the instruction queue, which is also known as reservation stations. Secondly, we have to take a look at the possible unifications inside the board. This platform merges the ARMs into a single pack while leaving the DSPs split. This makes them share the same bus and slave port in the multi-core shared memory controller, as it can be seen in these pictures. Therefore, from the point of view of an ARM, there will be not only interference in the SDRAM controller, but also before. Just before starting with the interference calculation, let me explain you how the data was obtained. To stress the SDRAM, micro-benchmarks were used. These contained either loads or stores, but not both at the same time. Besides, these instructions pointed to a given SDRAM address, more specifically to a concrete bank, column, and row. The execution was done asynchronously from the ARMs or DSPs, repeating indefinitely until the necessary data was captured. The interference that these micro-benchmarks produced to the transactions from the core under analysis were measured using three different systems. For the ARMs, it was used their performance monitor counters, where the execution time or bus accesses were obtained. For the DSPs, it was used their timestamp register to retrieve the execution time. To obtain information about what's happening inside the SDRAM controller, the controller performance counters were used. A large amount of information could be extracted, as you can see from the events list. Part of these events could be studied from a system or a core perspective. Now let's see how the interference calculation is done. We are dealing with read and write commands that, if you recall, have a priority difference. Hence, the behavior will not be the same when executing loads than when executing stores, which will require the elaboration of two different equations. Furthermore, we have to consider the number of different arbitrations due to the memory address we are accessing. We can distinguish three of them. First, we have what we have called the fixed block address. This arbitration is used when all the cores are accessing the same memory block. Second, we have the bank switching. This occurs when each core has a dedicated bank for itself. Third and last, we have the row switching. This one takes place when each core aims to a different row within the same bank. These arbitrations are further developed in the following slides. The final equations scheme is found below. For each arbitration, we have to estimate the received impacts from the read and write point of view, making a total of 6 equations. The fixed block address arbitration takes place when all the cores point to the same block address as shown in the image below. This arbitration causes the command queue or command FIFO in Texas Instruments nomenclature to behave as a first-in, first-out queue. Therefore, the commands are served in order, making the reads have the same priority than the writes. Let's consider the example at the right. The green-colored read command is the one under analysis. From its perspective, before being executed, the other 9 elements in the queue must be executed. Furthermore, it will suffer from turnaround delays, 2 from the 2 other load commands inside the queue, and the one provoked by itself. Step 2 and Step 3 show how the load command advances in order. The fixed block address arbitration is the simplest of the 3, therefore it will be used for explaining how the equations were elaborated. Let's assume that we have these 4 cores, 3 DSPs and 1 ARM. Our core under analysis is the core called DSP0, which executes load instructions which result in read commands. The others will act as sources of interference. The first thing we have to pay attention to is how many interfering commands are inside the command FIFO when one command from the core under analysis is enqueued. This situation is depicted with the following different cases that result from activating the cores one by one. Be aware that the DSP loads are much slower than the DSPs and ARMS stores. In the first case, our command will not be interfered as it is in isolation. In the second case, it will see that the FIFO is full of read commands as a result of enabling the DSP1. Here, our command suffers from a turnaround delay caused by itself. The third case shows the situation when having an interfering read command, which provokes an extra turnaround. The last case shows a possible behavior when adding the ARM core. The quantity of interfering commands inside the FIFO is returned by the function sGNCL, which uses the load and store execution time in isolation conditions for each type of core, plus the enqueuing policy. In addition, we need to add the operation execution time, which can either be the CAS latency for the reads or the CWL for the writes. We still need to consider the proportion of reads and writes inside the FIFO. This is computed by R1 and R2 for writes and reads respectively. Finally, for this arbitration, we need to be aware of the possible turnaround delays, which will only exist if both reads and writes are involved. Our read under analysis will automatically suffer from this turnaround as it will encounter a write. Moreover, our transactions will suffer from the possible interfering commands turnaround. The frequency of these turnarounds are computed by the function AHR, multiplied by the active cores executing loads. The bank switching arbitration takes place when each core aims to a different bank, as shown in the image below. In here, command reordering is produced. The command burst optimization is applied, which consists in making groups of writes and reads of a given size. In this way, the turnaround delays are reduced. The example at the right explains this situation. It can be seen a group of reads in blue and 2 others of writes. Our command under analysis, which is a read, is going to be enqueued. In step 2, we can see how this command skips the first group of writes in order to join the group of reads. In step 3, one of the groups of writes have been completely served, and now we proceed to execute the group of reads. The row switching arbitration takes place when each core aims to a different row within the same bank, as shown below. An open row policy is followed, meaning that all the commands belonging to an opened row must be executed before the commands of a closed row are carried out. This policy has an advantage, which is the reduction of the precharged and active commands that can heavily impact the performance. However, it is also responsible of possible starvation situations, where row switches are never produced, what blocks the commands from another row. To avoid this, a priority elevation mechanism is triggered every time the oldest command has been blocked for a configured time. At the right, we have one example which depicts how this arbitration works. The green commands are the ones under analysis. their row is already opened, what allows them to be executed with any kind of extra delays. However, the other commands belonging to different rows will suffer from the row switching cost. Step 2 shows how the command to enqueue from step 1 skips the other commands in the queue. The same situation happens in step 3. In this slide, it is shown two figures that compare the theoretical output of the equations, represented as an orange continuous line, and the measured execution time, shown as gray bars. The figure's y-axis represents the execution time per instruction from a specific core and command point of view. The x-axis shows the experiment that it is being conducted, which is defined by the cores being used, ARM or DSP, and the kind of instruction being executed, load or store. The figure at the left shows the interference impact from a write perspective, executed from a DSP. At the beginning, when enabling the different arms, there is no response, meaning that the DSP is not being interfered when increasing the number of arms. This is due to the unified ARM park slave. Independently of the number of arms, the DSP will only be affected by one request at a time. This would change if instead of arms we had DSPs, which each of them have their own slave port. Afterwards, when adding DSPs executing loads, it is seen how the execution time increases, mainly due to the turnaround cost. The figure at the right shows the interference impact from a read perspective, executed from an ARM. Note that the y-axis is on a logarithmic scale. The observed peak in the second experiment is the result of a continuous starvation. The continuous flow of stores from the DSP plus the limited number of concurrent loads a processor can execute lead to this situation. This does not occur anymore in the third experiment because there are two DSPs filling the command FIFO with the stores pointing to different rows. The store commands with the opened row are executed while the others accumulate until no more commands of the current active row are available. Consequently, a row switch is produced. The final experiments show how the execution time continues increasing due to the higher number of row switches produced by the new cores. Now we are comparing the theoretical and measured values of the different arbitrations with themselves. So in green we have the fixed block address, in blue the bank switching, and in orange the row switching. As in the previous slide, at the left we have the write perspective and at the right the read one. It can be observed how the row switching arbitration yields the worst results in both the scenarios. Of course, this is due to the precharged and active commands that we have to execute every time a new row has to be used. From the point of view of the reads, the bank switching reduces the interference the most thanks to the turnaround reduction. From the write perspective, it is the fixed block address the one returning the best results, as the reads can't preempt the writes, while in the other two arbitrations this happens. Through this work, it could be seen that it is possible to estimate the SDRAM interference impact in heterogeneous multicore platforms by focusing on three aspects. Firstly, on the SDRAM memory device, and hence model the JTAG specifications related to timing and operation. Secondly, the memory controller. The command's priority and its reordering as a consequence of the arbitration being applied are able to change the SDRAM behavior completely. Thirdly, the multicore platform heterogeneity, where we can point out the architecture asymmetries and the performance difference of the different types of processors. In real practice, the developed equations can be satisfactorily used when using one arbitration at a time, which is a scenario that can be found, for example, when having a perfect core bank mapping or when dealing with shared data placed within the same memory block address. However, it is frequent to find applications where many arbitrations are used at the same time. Therefore, it would be a good idea to continue this work by elaborating a new equation where all the arbitrations are represented. In addition, it would be interesting to study to which extent these equations could be used in other heterogeneous platforms. There are other papers about the SDRAM interference analysis. Among them, those that you may find interesting are shown here. The first paper proposes a DDR2 memory controller design that can upper bound the latency. The second paper studies several SDRAM controller architectures thought for real-time applications, which are analyzed through a benchmark suite and a simulation engine. The third work introduces a new perspective. It states that DDR DRAMs are not suitable for hard real-time systems because of highly variable access latencies and overly pessimistic latency bounds. In consequence, this paper focuses on the analysis of the reduced latency DRAM. We have arrived to the end of this presentation. Thank you for watching and have a nice day.